Monday, you have, I think, 3 or 4 objectives from this week. That's the normal part. That's nothing different than all the rest of life. Next week, in order to give you a substantial open pie time, the objectives from Monday and Wednesday, which are the last 2 teaching days, are due Friday at midnight. So that, on Wednesday, I don't know, whatever the Wednesday of finals is, maybe the 15th? That sounds about right. On the 15th, your pie is due at the start of class. So if you missed the deadline and you've turned in all of the rest of them on time, it's not a biggie. You just need to make sure your pie is done by the start of the final, which is the 15th at 3 p.m. I will send more announcements next week. And so next week we will cover chapter 10, which is gas laws. So more than likely prior to this, you've seen PV equals NRT. Maybe. Y'all are very still today. Stiller than you usually are. So that's what we'll talk about next week. Those objectives will be due on Friday. Shouldn't take all that long. As a reminder, your final exam is 200 points and it's cumulative, and it will take an hour and 50 minutes, which is the time slot. So it's like the midterm, except you have a few more minutes. Questions about any of this information?
So there's going to be an open pie from December 11th to the 15th?
Yes. The open pie is from the 11th through the 15th. Yes, that's exactly how that should work. For you to finish out anything you'd like. You can also, if you would like to get ahead, anything opens as soon as you finish whatever is due this week. So, any other question? I mean, I feel like at this point we know how Alex works. I wanted to highlight that it was going to change next week. Any questions before we get started? Hopefully you spent a little time between the last time I saw you and today looking at how to draw Vesper structures of more complex molecules, such as urea. So because I can't annotate on that one, I will redraw it on the board. So when we look at these types of molecules, whether it is the amino acid on the previous slide, urea, or any of the other complex molecules, so we draw eyebrows for real. It gets a little something different every day, and it brings me great joy. So now, what was I talking? Oh yeah, urea. So here we have 3 different central atoms. What you guys always want is that you would look at it and see it in 3D immediately. Your hope is actually, or the best plan of attack, is to start at one nitrogen or the other. So what is the steric nitrogen for this nitrogen, or the steric number for the nitrogen on the left? 4, which makes it a base tetrahedral. So we can start by just drawing that. So we're going to put our nitrogen in the center with wedges and dashes, and it looks a little bit like this. From here, we can then go ahead and add in our 2 hydrogens in a lone pair. Does it matter where anything goes? No. It will make your life easier if you put the carbon kind of in the center, but you can put it anywhere, and anywhere is sufficient. So I'm going to put my hydrogens here, my lone pair here, my carbon in the center. This has a steric number of 3. What are the bond angles for a steric number of 3? 120. So 120 is roughly thirds. So we're going to try to draw something that looks just like that. Again, it doesn't matter which of these is the oxygen and which of these is the nitrogen. I'm going to put my oxygen here, so that puts another nitrogen here. We get to do the same thing. It is also base tetrahedral. And there is no rational explanation But this rotates around this bond, and so you can actually add in your hydrogens and your lone pairs anywhere you like. So mine look like this. What questions do we have about drawing urea? Yeah.
So I did the line going off nitrogen and then the dashes and then I just on the other side. Is that the same thing pretty much?
Yes. So instead of this, your nitrogen. Something like that? Yeah, that's equally correct. These, it spins like a propeller, so you can put them almost anywhere you like. Mine just looks like that. Other questions? Yeah.
So you know how you're talking about when you made the line from nitrogen to carbon, you made it slice it down because of the 120 of the angle? When I did it,
This one?
when I did it, I just did it straight across, so that'd be incorrect, because it doesn't put into play the angle.
So is the nitrogen, carbon, nitrogen a straight line?
Yeah, like if I was to do that, I'd be wrong. So I
Mm-hmm. You need more. I will not use a protractor. If you use it on this, I'm pretty sure that none of these are exactly right. But you need more definition than what you see in that structure. So some sort of deviation that indicates that this is 120 and these are clearly not 120. So somewhere in between. But I don't want to say grade with grace. I'm not asking you to be a Nobel Prize winning scientist today. I'm just asking you to be a Gen Chem 1 student who's giving it, frankly, your best. Other questions? Oh, that's not number 2. So, for the next, bit, let's continue our discussion of the multiple bonds. So we talked about the hybridization of nitrogen, and we determined that these nitrogen atoms in the rightmost structure are sp hybridized. So if we look at ethylene, which is the central molecule, we have this. So both of these carbons have the same hybridization. What is that hybridization? We have a lot of hearing, or I hear a lot of things. So it's sp2. Now, the question becomes, do double bonds count as one thing or two? In terms of the steric number, they only count as one. So in this case, carbon has a steric number of 3. It is trigonal planar. The hybridization for both of these is sp2. When we think about this hybridization, when we talked about it on Monday, we talked about the leftovers. There is one singular p orbital leftover, right? Because the sp2 means we mix together one s and 2 p's, so we have a leftover. So the question becomes, what does that do? So a sigma bond is the bond between the 2 nuclei. And so we know that that's going to happen here. So I'm going to rotate this molecule in 3D space and get something that looks like this. So I took this flat molecule and basically flipped it this way. So we can think about the leftover p orbitals. Both of these carbons have one. And it turns out that they're in the same orientation. And they are both up here, above and below the plane. So we can create a pi bond above and below this internuclear axis. So we have sigma bonds. We'll say along internuclear axis and pi bonds They both mean that if this is the internuclear axis, it is above and below or in front of and behind. It is at 90 degrees to the central atom. So in this case, we have an sp2 hybridized carbon that has a remainder or a leftover p orbital. That p orbital gives rise to the pi bonds. All we're really doing today is taking the double bonds that we've known about for weeks and saying, hey, the way we get those isn't that there's twice as many electrons between the two nuclei. It's that you have the same number between the nucleus, but like a sandwich bun of extra electrons holding them together. Visualization, because my drawings are great, but it always helps when they're computer generated. So if we look at this slide, we can see the ethylene structure on the left. On the right, they have pink p bonds, or p orbitals. And we can see that they get substantial overlap, and so what we get is two p orbitals above these two carbons, above the internuclear axis, that leads to the pi bond, or the double bond. What questions do we have so far?
A double bond is a sigma and a pi, right?
Yes. And the triple is a sigma and 2 pi. Yeah. Orthogonal, but I'm not actually sure that I can spell it correctly, and so I kind of squashed it together in hopes that no one would notice. It's really too bad you don't have like spell check in real life. Did I spell it? Well, there are no other words. Yeah, I'm pretty sure it's missing a lot of things, but we could scratch it out and write perpendicular. You can just write whatever works for you. Other questions? So, in this case, we have a single pi bond that lives in this one place. The other thing with pi bonds is that they can become what's called delocalized. So let's look at benzene. Benzene is C6H6. And so the structure for that is a cyclic ring structure. And it looks like this. As we look at this, none of these carbons as of yet have octet. If you needed, or you count up all the valence electrons, you would have 6 left, and so we could create double bonds here. Alternatively, we could have put the double bonds in the other slots. I'm going to use what I hope is a very bright orange color, but we'll find out. Excellent. So we could have also had them here. So you could have either the black arrangement or the orange arrangement. What is the hybridization for all of these carbons? They're all sp2, which means they all have a leftover p orbital. So when we start to think about these two structures, we can create double bonds. So in this case, try not to make drawings where you can't see anything because there's like too much happening. So in this case, if all of these hydrogens have a leftover p orbital, which I will draw as circles, which you could imagine are sandwiched up top, what we see is a pi bond here. So the question is, we know that because there are multiple arrangements for the double bonds, we have resonance, right? So what resonance really means is that we have p orbitals that are arranged in such a way that the electrons could alternatively have been here, here, or here. Now I don't have a purple marker, so I can't draw a giant purple circle. We can imagine that. So it turns out that the resonance here turns into basically a circle of double bond, where all of these work together to create what's called a delocalized pi bond. Now, my drawings are terrible. Let's look at some graphics. So on the purple image on the left, those are our sigma bonds. So we can count those up. We can see that the entire center ring is that. The leftover p orbitals are shown on the right, and we can see that all 6 of them are oriented into the same space. There, I'll point out. We have 2 different localized pi bonds that you can see on the left graphics here. On the right, they become delocalized. All this is saying, it's not all this is saying, what this is showing you is that when the resonance structures occur, we talked about how you could get these hybrid structures, where instead of the observation of a double bond length and a single bond length, we saw 1.5 length bonds, right? That is due to the delocalization of the pi bond, because it's distributed evenly over all 6 bonds, as opposed to over 3, and then switching between the 2. So in order to have resonance, that we talked about in chapter 8, you have to have leftover pure p orbitals that are connected. Because realistically, the electrons in a delocalized pi bond, which is what resonance is, have to have the ability to create, I don't want to call it an electron superhighway because that sounds weird, but the ability to migrate from one bond to another, and they all have to be connected and oriented the same direction in space. What questions has this brought to the surface?
So that would only happen when the organization is SP2 or SP1?
Yes, so it's either SP or SP2. So SP3 doesn't tend to have hybridization and resonance at the same time, because there aren't any p orbitals left over. Any other, I don't want to call them burning questions, but regular questions?
So how you drew like the red and the blue is basically connecting the red?
So the blue correspond, I guess I could have used orange to be consistent,
Oh, okay.
but that would be the other alternative arrangement. Good question. So when we think about a bond, every bonded atom or bonded pair is connected with a sigma bond that is along the internuclear axis. These don't contribute to other bonds. So sigma bonds are basically, they have one job. They function as glue to hold things together. When the atoms share more than one pair of electrons, so in a double bond or a triple bond, the other pairs form additional sigma bonds. Additional pi bonds. So you get one pi bond and one sigma bond, or one sigma and 2 pi's. So multiple pi bonds have delocalization. This delocalization gives rise to the color that we find in LEDs. It gives rise to the color found in carrots, so beta carotene is what turns them orange. It has a resonance structure where they give off or generate an orange color. So when we think about this, more than likely, most of you have some level of a burning question. Where are we going to see this on the, it's not on today's mini exam, but on the final, what am I going to ask you to do? At this moment, with any structure, you should be able to quantify the number of sigma and pi bonds. You count them up. Just 1, 2, 3, 4, however many bonds there are. If it's a single bond, it's a sigma bond. If it's a double bond, it's 1 sigma, 1 pi. So we can do that. You should have a pretty good understanding of where resonance comes from. It is connected pi bonds, connected p orbitals that lead to pi bonds. Those connected orbitals can be delocalized. So delocalization occurs in resonance structures. You can also have a localized pi bond. That'll be like this. I thought that was mine. I was like, what? That's not even my alarm. So this is a localized pi bond. Localized just means it can't go anywhere else. You have to have more than one place for it to be delocalized. So let's think about the nitrate ion. So in this Lewis dot structure, Lewis dot Vesper structure, we see that there are 3 resonance structures. What is the hybridization of the nitrogen in these structures? It's sp2. What is the hybridization of the oxygen with the double bond? It's sp2 as well. So we clearly can see that those two have 2 p orbitals that give rise to the sigma bond, to the pi bond. So the question becomes, how do we have resonance if what we previously thought about says that the oxygen that does not have the double bond is sp3 hybridized, right? It has 4 things, 3 lone pairs, 1 bond. But we can tell that it's going to rotate around. So if we look at the orbital images, we see the sigma orbitals, those look great. But it turns out that all of the oxygens are sp2 hybridized. The ones with the negative charge, actually have 2 electrons in a p orbital, as we see in the top image. So we see what is actually distributed is less electrons overall. So what we see is that the 2 p orbitals at the top that both have a lone pair create a delocalized pi bond. This is when it starts to somewhat begin to break down. So the reality is, we're going to finish early today. So y'all don't have as many questions, and I don't think we should start chapter 10. So when we think about Lewis dot structures, we talked about those, we said these are great. And then we said, but some of these have more or less than octet. So Lewis dot structures started to, I don't want to say collapse, but they began to be not fully truthful. Then we moved to Vesper structures. Okay, now we can make molecules in 3Ds. We can then begin to think about that. But we also realized that the electronics, so where are the electrons, does not match with where the orbitals are. So then we started talking about hybridization. Hybridization tells us, okay, we took the orbitals and we remixed them and we made something else. As you can see with some of these, we start to see other contributions electronically. So many of you worked on the chapter 9 worksheet and looked at the sulfite ion, which is SO3 2-. So a structure looks like this. Where we have negative charges here and here. So we have the sulfite ion. So based on what we have talked about, the hybridization of the sulfur atom here feels like it should be sp3, right? It has 4 things connected to it, 3 oxygens and a lone pair. That's how we think it should be defined. But in the key, I said, does not hybridize. So how many electrons are around sulfur? 10. So those 10 electrons violate octet. So now all of the hybridization that we've talked about also no longer applies. So the reason we don't see hybridization of sp3d2 or sp3d is because the d orbitals are not energetically close to the p orbitals. It's kind of like saying, yeah, I could work here and only have like the copier or some room that you have to use on the 3rd floor without an elevator and no stairs. Like, I mean, they're there, you could use it. They're just not convenient. So in that case, we have used and created another system. It's called molecular orbital theory. Molecular orbital theory, or MO theory, looks at how molecules affect the mixing of orbitals. And they change the orientation of the orbitals and they mix them in different ways. In most semesters, we cover that in class. In this semester, I've taken it out because we are, as you all know, way behind where I thought we were going to go. But MO theory is the next step in trying to explain what we know to be true and observe. So we've evolved from Lewis dot structures to Vesper structures to hybridization to sigma and pi orbitals, sigma and pi bonds to MO theory, which basically expands upon that and explains how this nitrite ion is able to form using p orbitals that contain multiple electrons. So all of this is to say that there is no one right way to structurally create any of these things. Questions? What I believe we will do, since mostly you guys all look exceptionally comatose today, so you will still only have 35 minutes for the mini exam. We will just start now and end in 35 minutes, which is just prior to 5:45. I don't feel like anyone's going to be really sad about that. If you are, we can talk about it. It's still happening.